Hello all, my name is Manvita Reddy. Today I am going to deliver a presentation on NiagaraCQ, a scalable continuous query system for internet databases. These are the different topics we are going to cover in this presentation: abstract introduction, problem definition and challenges, proposed approach, implementation, related work conclusion, and then references. At first, we are going to discuss what this research paper is about, what this presentation is going to be on, what topic. Uh, Basically, at first, continuous queries are persistent queries that allows users to receive new results when they become available. While continuous query systems can transform a passive web into an active environment, they need to be able to support millions of queries due to the scale of internet. No existing systems have achieved this level of scalability, so that's the reason we have developed NiagaraCQ project. NiagaraCQ addresses this problem by grouping continuous queries based on the observation that many web queries share similar structures. Grouped queries can share the common computation, tend to fit in memory, and can reduce the input-output cost significantly. And furthermore, grouping on selection predicates can eliminate a large number of unnecessary query invocations. And the grouping technique is distinguished from previous group optimization approach in the following ways. First is they use an incremental group optimization strategy with dynamic regrouping. New queries are added to existing query groups without having to regroup already installed queries. Second, we use a query split scheme that requires minimal changes to a general purpose query engine. And the last one is NiagaraCQ groups both change-based and the timer-based queries in a uniform way. To ensure that NiagaraCQ is scalable, we have also employed other techniques, including incremental evaluation of continuous queries, use of both pull and push models for detecting heterogeneous data source changes, and memory caching. So basically, this presentation or this research paper presents the design of NiagaraCQ system and gives some experimental results on the system performance and scalability. Okay, now we will see what is Niagara project and the goal of this project. Continuous queries allows users to obtain new results from a database without having to issue the same query repeatedly. Basically, continuous queries are especially useful in an environment like the internet compromised for large amounts of frequently changing information. For example, users might want to issue continuous queries of the form. And the goal of the Niagara project is to develop a distributed database system for querying distributed XML datasets using query language like XML/QL, which is DFF plus 98. As part of this effort, the goal is to allow a very large number of users to be able to register continuous queries in a high-level query language such as XML/QL. We hypothesize that many queries will tend to similar to one another and hope to be able to handle millions of continuous queries by grouping similar queries together. Group optimization has the following benefits. First, grouped queries can share the computation. Second, the common execution plans of grouped queries can reside in memory, significantly saving an input-output cost compared to executing each query separately. Third, grouping makes it possible to test the firing conditions of many continuous queries together, avoid unnecessary invocations. Basically, this method can be used in real life, like in real-time environment where in companies or the stock exchange data. As you can see here, I've given a simple example like Dell and Micro stock exchange data. So basically, continuous queries can be classified into two categories depending on the criteria used to trigger their execution. Change-based continuous queries are fired as soon as new relevant data becomes available, and the timer-based continuous queries are executed only at time intervals specified by the submitting user. Like for example, in the day traders would probably want to know the desired price information immediately, while longer-term investors may be satisfied being notified every hour. Although change-based continuous queries obviously provide better response time, they waste system resources when instantaneous answers are not really required. Since timer-based continuous queries can be supposed to more efficiently, query systems that support timer-based continuous queries should be much more scalable. However, since users can specify various overlapping time intervals for their continuous queries, grouping timer-based queries is much more difficult than grouping purely change-based queries. This approach handles both types of queries uniformly. Now we are going to discuss the overview of NiagaraCQ. NiagaraCQ is the continuous query subsystem of the Niagara project, which is a net data management system being developed at the University of Wisconsin. NiagaraCQ supports scalable continuous query processing over multiple distributed XML files by developing the incremental group optimization ideas as introduced. A number of other techniques are used to make Niagara scalable and efficient, such as NiagaraCQ supports the incremental evaluation of continuous queries by considering only the changed portion of each updated XML file and not the entire file. Since frequently only a small portion of each file gets updated, this strategy can save significant amounts of computation. Another advantage of incremental evaluation is that repetitive evaluation is avoided and only new results are returned to users. The second one is NiagaraCQ can monitor and detect data source changes using both push and pull models on heterogeneous sources. Due to the scale of the system, all the information of the continuous queries and temporary results cannot be held in memory. A caching mechanism is used to obtain good performance with limited amounts of memory. And in this slide, we can discuss the command language of NiagaraCQ. NiagaraCQ defines a simple command language for creating and dropping continuous queries. Here you can see the command to create a continuous query, create continuous query name and then XML QL query, and then action do, and then you can see the field start time, time interval, expiration time, and the same to delete the continuous query, just delete and the continuous query name. So users can write continuous queries in NiagaraCQ by combining an ordinary XML QL query with additional time information. The query will become effective at the start time. The time interval indicates how often the query is to be executed, and a query is timer based if its time interval is not 0, otherwise it is change based. Continuous queries will be deleted from the system automatically after their expiration time. If not provided, the default values for the time are used. Action is performed upon the XML QL query results. Users can delete installed queries explicitly using the delete command. Now we'll discuss the problem definition and the challenges of this project. First we will see the problem definitions. In earlier existing continuous query system struggles to handle millions of queries efficiently due to the sheer volume of queries and the dynamic nature of web resident data. And there are other problems like many queries tend to share similar structures, but traditional optimization techniques are not applicable in the context of continuous queries, where queries are continuously added and removed. And traditional group optimization approaches are computationally expensive and not suitable for large number of dynamic queries. And continuous queries can be triggered either by changes in the data or at specified time intervals, each posing its own challenges for the efficient processing. Due to the scale of the system, holding all queries information and temporary results in the memory may not be feasible, necessitating the use of caching mechanism. Addressing these challenges or these problems requires innovative approaches such as incremental group optimization, dynamic regrouping, efficient query split schemes, and support for both change and timer based queries. Additionally, techniques like incremental evaluation of queries, monitoring data sources, using push and pull models, and memory caching are essential for achieving scalability and efficiency in continuous query processing systems like NiagaraCQ. Now we will discuss about the proposed approach provided in the research paper. Basically, increment group optimization strategy that scales to a large number of queries. This strategy can be applied to a wide range of group optimization methods. So here we have similar group optimization methods, which are general strategy of incremental group optimization using expression signature, query split with materialized intermediate files, incremental group of general selection predicates, and incremental grouping of join operators, grouping timer based continuous queries, and memory caching. We'll discuss each one of those in detail in the further slides. Now we will discuss about the first strategy of incremental group optimization. Basically, in this strategy, groups are created for existing queries according to their signatures, which represent similar structures among the queries. Groups allow the common parts of two or more queries to be shared. Each individual query in a group shares the results from the execution of the group plan. When a new query is submitted, the group optimizer considers existing groups as potential optimization choices. The new query is merged into those existing groups that match its signatures. Existing queries are not, however, regrouped in our approach. While this strategy is likely to result in suboptimal groups, it reduces the cost of group optimization significantly. More importantly, it is very scalable in a dynamic environment since continuous queries are frequently added and removed. It is possible that current groups may become inefficient. Dynamic regrouping would be helpful to regroup part or all of the queries either periodically or when the system performance degrades below some threshold. This is left as a future work. Now we are going to discuss another strategy, which is incremental group optimization using expression signature. It is a specific implementation of the signature concept. Here you can see the XML QL queries on a database of stock codes. The two XML queries retrieve stock information on either Intel or Microsoft. Many users are likely to submit similar queries for different stock symbols. An expression signature is created for the selection predicates by replacing the constant appearing in the predicates with a placeholder. The expression signature for the two queries is equals to symbol. This is expression signature of queries. A query plan is generated by a NiagaraQQ parser. Basically, this query plan includes trigger action and then selection statement, file scan, and the code XML file. Expression signature allows queries with the same syntax structure to be grouped together to share computation. Expression signature in NiagaraCQ users can specify an XML QL query without specifying the destination data sources by using a star in the file name position and giving a DDT name. This allows users to specify continuous queries without naming the data sources. The group query optimizer is easily extended to support this capability by using a mapping mechanism offered by the Niagara search engine. The groups are created for queries based on their expression signatures. Here, first one is group signature. The group signature is the common expression signature of all the queries in the group. It does have constant value at the destination buffer. And the group constant table contains the signature constants of all the queries in the group. And the constant table is stored as an XML file. And the group plan is similar to the query plan shared by all the queries in the group. It is derived from the common part of the single query plans in the group. Now we'll see in detail about the query split with the materialized intermediate files. The destination buffer for the split operator can be implemented either in the pipeline scheme or as an intermediate file. The initial design of the split operator used as a pipeline scheme in which doubles are pipelined from the output of one operator into the input of the next operator. In the pipeline approach, the ungrouped parts of all the query plans in group are combined with a group plan. This single plan has several disadvantages. First, its structure is a directed graph and non-arbitrary. Thus, the plan may be too complicated for general purpose the XML QL query engine to execute. Second, the combined plan may be very large and the required resources beyond the limits of some systems. Finally, a large portion of the query plan may not need to be executed at each query invocation. Here you can see the query split scheme using intermediate files. Since a split operator has one input stream and the multiple output streams, split operators may become a bottleneck when the ungrouped parts of queries consume output tuples from the split stream at widely varying rates. For example, suppose 100 queries are grouped together, 99 of which are very simple selection queries and one is which is very expensive query involving multiple joins. Since this expensive query may process the input from the split operator very slowly, it may block all the other simple queries. This pipeline scheme can be used in systems that support only a small number of change-based continuous queries. Since our goal is to support millions of both change-based and timer-based continuous queries, we adopt an approach that is more scalable and easier to implement. We also try to use a general query engine to the maximal extent possible. In our new design, the split operator writes each output stream into an intermediate file. A query plan is cut into two parts as the split operator and the file scan operator is added to the upper part of the plan to read the intermediate file. NiagaraCQ treats the two new queries like the normal user queries. In particular, changes to the intermediate files are monitored in the same way as those to ordinary data sources. Since a new continuous query may overlap with the multiple query groups, one query may be split into several queries. However, the total number of queries in the system will not exceed the number of group plus the number of original user queries. Since we assume that no more than thousands of groups will be generated for millions of user queries, the overall number of queries in the system will increase only slightly. Intermediate file names are stored in the constant table and group continuous queries with the same constant share the same immediate file. And we have some advantages of this new design. Like each query is scheduled independently, thus only the necessary queries are executed. And queries after a split operator will be standard tree structured query format and thus can be scheduled and executed by a general query engine. Each query in the system is about the size of a common user query so that it can be executed without consuming an unusual amount of system resources. This approach handles intermediate files and original data sources files uniformly. Changes to materialized intermediate files will be processed and monitored just like changes to the original data files. The potential bottleneck problem of this pipeline approach is avoided. However, there are some disadvantages as well. First, the split operator becomes a blocking operator since execution of the upper part of the query must wait for the intermediate files to be completely materialized. Second, reading and writing the intermediate files occurs extra disk input outputs. Since most data changes would be relatively small, we anticipate that they will be buffered in memory before the upper part queries consume them. Now we'll discuss about incremental grouping of general selection predicates. The primary focus is on the predicates that are in the format of attribute OP constant. Attribute is a path expression without wildcards in it. OP includes equals to, less than, or greater than. Such formats dominate in selection queries. Other predicate formats could also be handled in the approach, but we'll discuss them later. A general range query has both lower bound and upper bound values. Two columns are needed to represent both bounds in the constant table. Thus, each entry of the constant table will be lower bound, upper bound, and intermediate file name. The join condition is change ratio less than upper bound and change ratio greater than upper bound. A special index would be helpful to evaluate this predicate. The first one, you can see the range selection query example and its expression signature. Our potential problem for range query groups is that the intermediate files may contain a large number of duplicate tuples because range predicates of the different queries might overlap. Virtual immediate files are used to handle this case. Each virtual immediate file stores a value range instead of actual result tuples. All the outputs from the split operator are stored in one real intermediate file which has a clustered index on the range attribute. In general, a query may have a multiple selection predicates, that is multiple expression signatures. Predicates on the same data source can be represented in conjunctive normal form. The group optimizer chooses the most selective conjunct which does not contain or to do incremental grouping. Other predicates are evaluated in the upper levels of the continuous query after the split operator. Here in this example, which showed two predicates which retrieves Intel stock whenever its price falls below 100. This query has two expression signatures. One is equal selection predicate on symbol and the other is a range selection predicate on current price. The expression signature on the equal selection predicate is used for grouping because it is more selective. Now we will discuss about the incremental grouping of join operators. Since join operators are usually expensive, sharing common join operators can significantly reduce the amount of computation. The signature for the join operation. Here you can see in this picture a join signature in our approach contains the name of the two data sources and the predicate for the join. The group optimizer group join queries with the same join signatures. A constant table is not needed in this case because there is only one output intermediate file whose name is stored in the split operator. This file is used to hold the results of the shared join operation. There are two ways to group queries that contain both join and selection operators. For example, in this box, which retrieves all the stocks in the computer service industry and the related company profiles, the group optimizers can place a selection either below or above the join so that two different grouping sequences can be used during incremental group optimization process. The group optimizer chooses the better one based on a cost model. And the next one is grouping timer-based continuous queries. Timer-based queries are only periodically executed. Their use can significantly reduce computation time and make the system more scalable. We have two different types, event detection and the incremental evaluation. Two types of events in NiagaraCQ can trigger continuous queries. They are data source change events and timer events. Data source can be classified into push-based and pull-based. Push-based data sources will inform NiagaraCQ whenever interesting data is changed. On the other hand, changes on pull-based data sources must be checked periodically by NiagaraCQ. And the next one is incremental evaluation. Incremental evaluation allows queries to be invoked only on the changed data. It reduces the amount of computation significantly because typically the amount of changed data is smaller than the original data. For example, for each file on which continuous query is defined, NiagaraCQ keeps a delta file that contains recent changes. Queries are run over the delta files which are possible instead of their original files. However, in some cases, the complete data files must be used. For example, incremental evaluation of join operators. NiagaraCQ uses different techniques for handling the delta files of ordinary data sources and those of intermediate files used to store the output of the split operator. In order to support the timer-based queries, a timestamp is added to each tuple in the delta file. Since timer-based queries with the different firing times can be defined on one file, the delta file must keep data for the longest time interval among those queries that use the file as an input. And the last one is memory caching. Due to the desired scale of the system, we do not assume that all the information required by the continuous queries and the intermediate results will fit in memory. Caching is used to obtain good performance with a limited amount of memory. NiagaraCQ caches query plans, system data structures, and data files for better performance. Grouped query plans tends to memory resident since we all assume that the number of queries groups is relatively small, and the non-grouped change-based queries may be cached using an LRU policy that favors frequently filed queries. NiagaraCQ caches recently accessed files. Small delta files generated by split operators tend to be consumed and discarded. A caching policy that favors these small files saves a lot of disk input-outputs. The event list for monitoring the timer-based events can be large if there are millions of timer-based continuous queries. To avoid maintaining the whole list in memory, we keep only a time window of this list. The window contains the front part of the list that should be kept in memory within 24 hours. Now we are going to see the implement and the system architecture of NiagaraCQ. Basically, NiagaraCQ is being developed as a subsystem of Niagara project. The initial version of the system was implemented in Java JDK 1.2. A validating XML parser from IBM is used to parse XML documents. And the system architecture, NiagaraCQ is a subsystem of Niagara that handles continuous queries, and it consists of a continuous query manager, which is the core module of NiagaraCQ system. It provides a continuous query interface to users and invoke the Niagara query engine to execute fired up queries, a group optimizer that performs incremental group optimization, and an event detector that detects timer events and changes of data sources. In addition, the Niagara data manager was enhanced to support the incremental evaluation of continuous queries. And it also has the processing continuous queries. Uh, Here it shows the interactions among the continuous query manager, the event detector, and the data manager as continuous queries are installed, detected, and executed. Continuous query installation. When a new continuous query enters the system, the query is passed and the query plan is fed into the group optimizer for incremental grouping. The group optimizer may split this query into several queries using the query split scheme. The continuous query manager then invokes the NiagaraQQ optimizer to perform common query optimization for these queries, and the optimized plans are stored for future execution. Timer information, data source, name of these queries are given to the event detector. The event detector then asks the data manager to monitor the related sources files and intermediate files, which in turn catches a local copy of each source file. This step is necessary in order to detect subsequent changes to the file. The event detector monitors two types of events: timer events and file modification events. And the data manager in Niagara monitors web XML sources and the intermediate files on its local disk. Basically, it supports both push-based and the pull-based data sources. For push-based data sources, the data manager is informed to a file change and notifies event detector actively. Otherwise, the event detector periodically asks the data manager to check the last modified data. And it also has the continuous query deletion. A system unique name is generated for every user-defined continuous query. A user can use this name to retrieve the query status or to delete the query. Queries are automatically removed to the system when they expire. And the last one is execution of continuous queries. The invocation of a continuous query requires a series of interactions among the continuous query manager, event detector, and the data manager. When a timer event happens, the event detector first asks the data manager if any of the relevant data sources have been modified. The data manager returns a list of the names of modified source files. Also notifies the event detector when push-based data sources have been changed. Then the continuous query manager invokes the Niagara query engine to execute the triggered queries. At the execution time, the query engine requests data from the data manager. Then the data manager recognizes that it's a request for a continuous query and returns only delta file. Delta files for source files are computed by performing an XML def operation using the original file and the new version of the file. Now we will discuss about the related work. Terry had first proposed the notion of continuous queries as queries that are issued once and run continuously. And then the Triggerman project proposes a method for implementing a scalable trigger system based on the assumption that many triggers may have common structure. There are still have differences between NiagaraCQ and the Triggerman approach. The first one is NiagaraCQ uses an incremental group optimization strategy, and the NiagaraCQ uses a query split scheme to allow the shared computation to become an individual query that can be monitored and executed using a slightly modified query engine. And NiagaraCQ supports grouping of timer-based queries, a capability not considered in Triggerman approach. And other one is Sally's work focused on finding an optimal plan for the small group of queries by recognizing a containment relationship among the selection predicates of queries with both selection and the join operators. And at last we conclude that the goal is to develop an internet scale continuous query system using group optimization based on the assumption that many continuous queries on the internet will have similarities. Previous group optimization approaches consider grouping only a small number of queries at the same time and are not scalable to millions of queries. Then they have proposed a new incremental grouping methodology that make group optimization more scalable than the previous approaches. This idea can be applied to very general group optimization methods. They also propose a grouping method using a query split scheme that requires minimal changes to a general group proposed query engine. And in the system, both timer based and the change based continuous queries can be grouped together for event detection and group execution, a capability which is not found in other systems. And the preliminary experiments demonstrate that the incremental group optimization significantly improves the execution time comparing to non-grouping approach. And here are the list of references that we have used. I have used for this presentation. Thank you.